Hello everyone, welcome back to the tutorials on the mechanical vibrations. Today we start a new topic, which is the free vibration of single degree of freedom systems, and we're going to have multiple tutorials on this topic. So in the first tutorial we introduce the concepts and we try to solve two examples on that. We start with a very simple example and then we go to a more complicated case. So let's begin. Okay, so as usual, let's have a very quick review on the contents and what a single degree of freedom system means. So to start with, normally we can write down a single degree of freedom as the case that we have only one degree of motion or freedom for the equivalent mass of the system. The most simplified case is when we have, for example, a spring and a mass. So M and K, and as you see, there is no damping for the system and there is no basically force in the system. So if this is X is basically the degree of freedom and shows our one degree of freedom, and that's why we call it a single degree of freedom. If we have a damping in the system, then the system is not undamped, and a damping, for example, a damping appears in the system like this, right, with the damping coefficient of C. But for today, we only focus on the undamped system. So remember, we have an undamped single degree of freedom system for the examples for today. So in many cases that we have an undamped system, we want to simplify the system to this case when we have a spring and a mass, but K is the equivalent stiffness and M is the equivalent mass. You remember, we will be able to find the equivalent stiffness from the force or newtons or the series and parallel connections, or from the potential energy formula. For equivalent mass, we can also use the Newton's rules, or we can use the energy method, but this time we can use the kinetic energy. So the kinetic energy of, let me just use the kinetic energy formula here. So in fact, we're going to use the T, not U, right? That was my mistake. So we can write the T equal, I'm using the shaded area. Let me use another one. So we have T is equal to T1 plus T2 plus whatever. So T is basically the kinetic energy of the equivalent mass, and V is the speed or the velocity, and then T1, T2 belongs to all the masses which are linearly dependent to each other, right? So I don't want to go more into the details, but you can see more examples and how we can derive the equation, right? So let me see if we have a single degree of freedom and what is the equation of motion. In the most simplified case, when we have the system ended to this shape, we have equivalent stiffness and the damping, so we have K EQ and M equivalent. The equation of motion would be as M equal X double dot plus K equal X equal to 0. And as you see, X is the degree of freedom, and for the second order degree of basically equation or a second order differential equation like here, we need two initial conditions. The initial displacement X naught and the initial velocity X dot naught, right? So if we solve this, we can end up into a harmonic function. So xt would be as a sine, for example, omega n t plus b cos omega n t, right? A and b are obtained by applying the initial conditions. And what is omega n? Omega n is the natural frequency, which is a very important parameter for the free vibration analysis, which is equal to K EQ to M EQ, right? So this is the natural frequency of the system. You can hear this in the future, and we are going to use omega n a lot for free vibrations of single degree of freedom systems and even higher degree of freedom systems, right? So let's start our first example, which is a simplified case. Okay, let's go over this example and start solving that. As you see in this example, we have an air conditioning unit shown in the picture rested on 4 air springs. For simplicity, we can consider that the air springs are like coil springs, or they have a linear force displacement relationship. So we can suppose that there is a huge mass rested on 4 springs at each corner, right? So this is the mass on 4 springs, right? And we need to find the natural frequency or omega n of the system such that the frequency is in this range. So in fact, it is like a design problem. We want to find the appropriate K value for the stiffness of the 4 springs so that the natural frequency is in this range, right? Let's see how we can do that. As you may remember, I said that we want to end up the system into a mass and equivalent stiffness case, and then we can use the omega n formula, which is equal to K over M. In this case, we have 4 springs, but if we look at this case more closely and we consider the mass as a block with 4 springs, like this one, that one, and this one. So we have 4 springs. They are all equal, K, 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 and K. So for this case, let me use K equal and K equal. And as you see, there is only one mass, so we don't have to be worried about the equivalent mass, right? And this is M. So if we look at this system, the degree of freedom is in this direction, and the system can be sort of simplified as the above shape, right? So as you look at this system, we have 4 springs which are in fact in parallel, right? Why? Because the X or the deflection is equal for all 4 springs. So we can simplify it using the parallel series connection formula that we have before. So let's see how we can do that and simplify the system. If we have 4 springs and they are all in parallel, the equivalent stiffness is the summation of the 4K, right? So the system would be as basically this case, right? But the K equal would be 4K, right? Very easy. Now let's continue on that. So we ended up into this system. We have the mass, and then we have the spring, 4K. And as you remember, the equation of motion for this system was M equal, which is actually M here, X double dot, and K equal, which is 4K, X equal to 0. And the natural frequency, omega n, is equal to the square root of K equal over M, which is 4K over M, right? Whatever is the coefficient of X is our K equal, and M, or the coefficient of X double dot, is our M equal. And therefore, the natural frequency would be the square root of 4K over M. So the problem says that we need to have omega n between 5 to 10 radian per second. And remember, the dimension or the unit for omega n must be always radian per second to satisfy the units and the dimensions. And the mass must be as kilogram. And in case we are using the K, it has to be Newton per meter, right? So remember this because we are going to use that in the future. Okay, so by all these considerations and calculations, we can simply find K. Let's look at omega n. Omega n is actually equal to square root of 4K over M. So if we square the two sides of this equation, we have omega n squared is equal to 4K over M, right? I'm using this equation. And then if we use more calculations, we get K equals to M omega n squared divided by 4. Very easy, right? I just use the cross multiplication and divide it by 4. So we also need to satisfy this condition, right? So let's use 5 as omega n and find k based on this equation, and then use 10 into this equation and find k. So if we plug in 5 and 10 as the lower bound and upper bound of the natural frequency, we can calculate k. And remember, m was given in the problem. The mass was 20,000, so m was 20,000 pounds. So we have to convert it to kilogram, which is very easy. We just multiply it by 0.453, which is equal to 907 kilogram. I'm sure that you can simply find it and calculate it, right? So using 5 as the lower bound of natural frequency and 10 as the upper bound of natural frequency in this formula, so I'm going to use formula 1. So 5 and 10 into formula 1, we can calculate k as 5,668.7 Newton per meter and k as 22,675 Newton per meter. So we will be able to find the upper bound and lower bound of k. So k must be between these two values. So k must be between, I would say, k lower bound and k upper bound. So k lower bound and k upper bound. So we will be able to design the stiffness of the air springs for the air conditioning unit so that we ensure that the natural frequency remain in this range, right? Very simple. So as you noticed, this is a very simplified case. Now we want to move to a more complicated example. So let's do it. Let's go over this problem and then start solving that step by step. Okay, I hope you have already reviewed the problem statement so that we can start that. So as you see, in this problem, we have a more complicated case and we want to find the natural frequency of the system. But first, we have to derive the equation of motion so that we can simply find the natural frequency of the system, right? So let's do it. So in order to do that, let's take a closer look into the shape that we have. As you see, we have a rod or a rigid bar, which means that there is no deflection in the rod. So remember, we have the word rigid, which means that the elasticity or the stiffness of the rod or the metal bar is neglected in the problem. However, we have two linear springs, K1 and K2, and we have a torsional springs in the system. And also, the rod or the bar has a mass m, which also associated with a moment of inertia, right? So we need to find the equation of motion first. How can we deal with these types of system? We may use the energy methods or we can use the Newton's law. I can use the Newton's law here, but for the Newton's law, we have to see which equation we are going to use, whether we are using the force or the moment rules. For this case, I write Newton's law or the second law of Newton, and we are going to use the moment formula. And for this case, we used point O as the reference. So as you may remember from the dynamics, we can write sigma m with respect to point O, which is the summation of the all existing moments due to the external terms, is equal to J O theta double dot. What is JO? JO is the mass moment of inertia of the bar or the metal rod, and theta is the degree of freedom, right? So how can we find JO first? JO is equal to a formula that you can find in the datasheet, but if we want to find it, so imagine we have an identical or non-identical shape and the shape is pinned at an arbitrary point, for example at the point O, and we know that the CG is located somewhere, for example here. This is the center of gravity, and the distance between the point pinned and the center of gravity is R, right? So this is R. So J with respect to O is equal to the J CG, which is the mass moment of inertia with respect to the center of gravity, plus mr squared, right? Which R is the distance from the pinpoint and the center of gravity. For this rod, we can simply write JO is equal to JCG plus, what is the distance between the CG and O? The half of the length of the rod, which is ML divided by 2 squared. And for a rod, CG is basically 1/12 of ML squared. You can find it in some tables or formula sheets. So simplifying this gives us 1/3 of ML squared. So as you see, we are fine with the right hand side of this equation. We have JO times theta double dot. What we need to find is the summation of all external moments in the system. Then we can use the Newton's law to simplify and finally find the natural frequency of the system. So let's do that. So to do this, let's draw the free body diagram of the system and see what are the acting moments in the system. So if I do that, so this is the bar. We have, if theta is in this direction, it pushes these linear springs downward, which means that there is a force acting on the opposite side, right? Which is this way, which is equal to K2 delta 2. And delta 2 is the deflection of the spring. I will find it out later, right? And regarding the other basically spring, which is K1, based on this theta, we are pulling the spring, which means that there is a force opposing that, which is K1 delta 1, right? But it's not the end. We also have a torsional spring which applies a torque in the opposite direction of rotation, right? Which is KT, and this is a torsional spring, so this is KT theta, right? Why? Because theta is the angle of rotation. So one thing that we need to find is the deflection of the spring for each one, right? How can we find that? So this is the deflection based on a small angle of theta, and if you look at it closely, this is nearly equal to this length times theta. In fact, it is this length times the sine or tan theta. However, for a small angle of rotation, which is the assumption for this problem, we can suppose that delta 1 is equal to A theta, right? Where A is the distance from the pinpoint to the location of the spring. For the other one, delta 2, which is here, it is nearly equal to the whole length times theta, right? Again, it is actually the tan or sine theta, but for a small angle. So if theta is, say for example, small, and by small means theta is less than or equal to 6 degrees, which is an assumption for this problem, the sine theta is equal to the tangent of theta, which is nearly equal to theta. And that's why we can suppose that delta 1 and delta 2 are nearly equal to the length to the location times the angle, right? So now we have all the forces, and we have to go back to our Newton's law, which was sigma m with respect to O is equal to JO theta double dot, right? So let's write down all the moments acting on the system and summarize everything into one equation. So I'm gonna use JO theta double dot is equal to, what is the first moment acting on the system? The moment due to the torsional spring, which is in the opposite direction of the angle of rotation, right? Theta is clockwise, but this moment is acting in the opposite direction. Why? Because always a spring is acting on the opposite direction of motion. So we have minus kt theta, right? Why minus? Because it is in the opposite direction. Minus the other force and the resulting moment from the first spring. So this force is basically creating a moment which is again against the rotation of motion. That's why we have this minus here. So we have k1 delta 1 times the arm of moment, which is A, right? So we have k1 delta 1 times A, right? And for the last force, which is because of this spring, again it is opposing the rotation, we have minus k2 delta 2 times L, because the arm of moment is L, right? So we can further simplify this equation. I'll do that in the next slide. Okay, so we ended up into the Newton's formula, and we got J O theta double dot equals to minus K T theta minus K1 delta 1, which was A theta times A, minus K2 times L theta, which is actually delta 2 times L. So if I simplify it and then put everything to the left hand side, and instead of JO, I'm gonna use 1/3 of M L squared theta double dot plus K T theta plus K1 A squared theta plus K2 L squared theta equal to 0. Let's look a closer look into this problem or this equation. So we have A here and A there, that's why we have A squared, and we have K1 and L times L, L squared, K2, and everything goes to the left hand side, so the sign changed to positive. Now we can factor out theta and further simplify it. So we have 1/3 of M L squared theta double dot plus, I'm gonna factor out theta, you have K T plus K1 A squared plus K2 L squared times theta equal to 0. So if we have a closer look to this equation, and by knowing that for a single degree of freedom we ended up to M x double dot plus K x equal to 0 for a linear motion or a translational motion, and for a rotational motion we have J theta double dot plus K T, or torsional, basically theta equal to 0. So let me just not use KT here, do not confuse it with the KT we have. So I'm gonna use basically, I don't know, KT or something. Let's look at a closer look and see how these terms are similar to each other. So we have this as this J. Oh, so I'm gonna use J EQ. So this is J EQ, and then this is K equal, and which is here, right? This is the coefficient of theta, like there, right? So this is K equal. So by all these assumptions, we can simplify the natural frequency of the system. So let's do that. So what we got here, we got this formula at the end, right? We found J equal theta double dot plus K equal theta equals to 0. So what is omega n? As you remember, we have k equal over j equal. And what is j equal here? It is equal to 1/3 of ml squared. And what is k equal? We have kt, the torsional stiffness, plus k1 a squared plus k2 l squared. And why we have this squared? So you might be asking about the unit. That's true. This k is a linear stiffness constant. However, kt and k equal is the torsional stiffness constant, so that the dimension will match. So if we plug in these two relationships into the above equation, we can simply find the natural frequency of the system. We don't have any numbers or values, so we don't continue on the calculation. However, we will be able to find the equation of motion of the system, which is here using the Newton's law and the Newton's law for the moments. And we also found the equivalent parameters, and finally the natural frequency of the single degree of freedom system. And as you see, in this system there is no damping or something. So that's everything for today's examples, and in the future we are going to have further examples and finding the response of the system and analyzing that for better understanding of the system. So thank you and stay tuned for the next videos.